Oh! Hello everyone, June the 10th. Alright, we haven't had a difficult problem for a while. A snapshot array. Implement a snapshot array that supports the following interface. Initialize an array with a given length. Okay, each element is 0 initially. Sets the elements at the given index to equal to val. Snap takes a snapshot of the array and returns the snap ID, the total number of times we call snap, -1. Int get returns the value at the given index at the time we took the snapshot with the given snap ID. I think I know what it's trying to do. So we set length to 3 and we can snap. No. We set at 0 position 5. Right, index is 5, and then we call snap, and we get an index. Wait, hold on. So we do this, and we set, and then we take a snapshot, return snapshot ID 0, and then set this. Now we'll get the value. Shall return 5 because at snap ID 0 the value is 5, but at snap ID 1, because we set it again, right? At snap ID 1 it becomes a different value. So what this just means, at each snap ID we need to know what value is, but we definitely cannot store all of them. Right? So what we need to do is for each value, for each index, we have a snap ID. The first set, right? We get a snap ID is 0. At this index, at the snap ID 0, what is the value? Right? And then you set again. So let's say at snap ID 100, then we get another value. How do we translate that? Well, we translate that by appending. So we can do something like this, right? We can do something like this. Let's try this. It's not even this, right? It's just it's an array. Okay, this is each position. Right? And at each position, what we need is a dictionary, which is say your snap ID. Initially, snap ID, we can say, wait, can we? Zero. Snap ID is 0. Everybody is 0. Okay? And then we set 1. Right? So everybody's like this. Everybody's like this. And then you set at a 0 position, you set a value to 5. So at this one, in particular, we change it. Right? You say, no, that's not it. Let's redo it. I want a list. Okay, I want a list with what? With snap ID and value. Everybody's this. And then at this position, we'll set a value. So snap ID, damn it. I mean the initial snap ID. Leave it there. I'll deal with it. Yeah, just put it there. Maybe initial one should be -1. How about that? Let's do -1. Everybody starts with -1. Okay? So for this position, the same. We'll start with -1, 0. That's the initial value. And then you set this to be 5. So we say snap ID 0 has value 5, right? And then we set it again. Snap ID 1 has value 6. Okay. And then we say, well, get the value. Index 0. So we look at this and we'll get snap ID. So snap ID with binary search, right? Binary search, we find, boom, we find it. If we have, let's say, something like this, 100, 1, right? We add snap ID 100, we get a value of 1. And we want to find the snap ID, let's say 50. Then you binary search this, you'll end up here. So we say it's going to be previous one, this value, because this value basically just continues throughout whatever. So this shall work. And given, I think yesterday, the problem is also binary search. So this is most likely right. I think we're in the binary search section for the current days. Just gonna have lots and lots of arrays and lots of binary search. And of course, we have to also, so what we need to do is a array. We can say self.array shall equal to for this in length, not in length, in range, length, and each one will start with a -1 0. Let's use tuple. That is not true. We want each one to be in a, is this. Okay, each one is going to be a list of tuple. That is right. And then we also need to say self dot what's that? Snap ID equals 0. Okay? And then set. How do we set? Index. So we say self dot array index dot append self dot snap ID value, and then snap ID plus equal 1. Okay, so when we return the snap, we take a snapshot. We need to return the snap ID to 0, but in this case, it'll be wrong. So what do? We set the snap ID to be -1. And we increment it first, then do it. And then we can just return self.snap ID. Now get, we require bisect. Right, we'll do bisect right. What do? Index. So we can get the array out. It's going to be self.array index. Right? This will get array out. And then we're going to do bisect right with snap ID. And we'll do a key. We will compare 0. So this will give us an index. This is the index within this array, right? And then we're gonna do, if it matches, so we go bisect right, so we can go to the right one. So we say index -1 is going to be the value. So what we're gonna do is return self.array index -1 1. All right, let's give this for a ride. What do we have? Looks about right. Let's give this a shot. Oh, damn, we've done this before. Ooh, that was bad. Because last time took 2 days. Okay, what was the problem? What was this problem? Why is it not right? What did we misunderstand? Okay, set, oh my god, snap array is 1. Okay, so in my case, it's only one value, and it's gonna be an array. We set -1, 0. Okay, when the set 0 equals, hold on. Well, set, because one can set this, so snap ID 0, 4, snap ID 1, 16, snap ID 2, 13. Okay, set, and then do snap. Set. How does this... Enjoy. Let's see. How is the snap 0? Did we understand the problem wrong? What does the snap return? Take a snapshot. Oh, my bad. I misunderstood it. Damn it. I misunderstood it. When you take a snapshot, you increment the snap. When you set, you just set. Alright, that was completely wrong. Alright, that's fine. So we don't do anything here. We do not do anything here. Now we just set the value. Oh, then it's different, right? We set the value. We can set however many values you want. And then we snapshot it. Once we snap it, that's when we take the snapshot, return an ID, which is the current ID, right? We need to redesign this. That's okay. We set to 0, okay? And this is gonna be a, because we need to change it. So when we set, don't change this. We do this, we do not append. Because we need to change the previous value. And when we snap, we take a snapshot, we increment the snap ID, so we need to check, right? We need to check. That's okay. So this is fine. So we don't. Well, it depends on the current snap ID, right? Depends on current snap ID. We say if self.snapID is equal to self.array index, the last one, 0. If it's equal, then self.array index -1, 1, we just change it into the value. If it's not equal, then, which means the current snap ID is incremented, then we say this dot append, we have to do something like this. And when you snap, in fact, I still think this is -1. When you snap, we say self.snapID. Here, when you snap, we need to plus equal 1. Right? We need to plus equal 1. And whatever the value everybody is at, you know what? No. I think it's still 0. We start with this, everything is 0. And then we'll change. And then when you snap, this one is going to plus equal 1, and we return -1. Right? We return -1. This is the snap ID, current snap ID. And everybody is up to date with this. And then when you do it again, the snap ID will be different. So you have to do other things. But what if you take, right? You take a snapshot. You just set. You take a snapshot, all right? Then everybody currently is good. And then you set. You set again. You set some value again. And then because now the snapshot has incremented, so those has to append a new value, right? Has to append a new value. And then you snapshot again. and those has, yeah, I think this should be right. And then you get, I think the get basically is the same thing. Okay, let's try this one. Slightly different. It's because my understanding of the problem was wrong. So let's see if this one's right. Looks more promising. Yep. I think we've improved from 2019. Jeez, that was a long time ago. I think this one I probably didn't solve it. Bisect, yeah. Yeah, yeah. Yes. Yes, yes. Yes, exactly the same. That's the improvement, right? For how many years? 4 years. 4 years of doing LeetCode. Shall be able to do this. Binary search. Let's do for each index, right? For each index, we keep an array of snap ID and a value pairs. And when querying an index and a snap ID, we use binary search to find the value, right? Basically, find the value. That shall be it. We use a binary search for the snap ID to find the value that lies between the previous snap ID and the current snap ID. Okay, so log n for get. That's not bad. Old problem, but haven't done this for a long time. What was my previous method? I'm curious. That was a long time ago. 3 years and 10 months. What was I trying to do? I think, oh, I was copying. Nah, this is not gonna work. Copy is not gonna work. There's a time limit. I'm joining. Oh, I'm trying to turn each array into a string. Man, I was pushing. The struggle was real. What is this one? Don't know. Similar things. Yeah, this is a binary search. But it was very green back then. 2019, August 2019. What I was doing, August 2019. I think I was in my first internship, August 2019. Binary search. Yep, exactly. That's the one, right? You don't have to record everything, just need binary search. They didn't even do... Oh, the number of calls, that's fine. They didn't even do the check. Do you not need to do the check? They just self the ID. Every time they call, we just self the ID. What if I set again? You just, same ID, keep going. And then You do bisect right. I don't know. Is this right? Holy crap, it is right. But this definitely will take more space. Yeah, you do keep adding on because the only one that matters is the last one, right? So you don't really worry about the previous one. You only do the index -1. Yes, this one works, but this is more space, saves more space. Binary search. All right, so we're done with this one. We have to come back to this, and that was yesterday's stuff. So we did a binary search, but it's not the most efficient. Let's see, Lee 215 minimax. You sort A. Yes. 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 K0I1. What are we doing? Oh, yeah. I think I thought about this yesterday. Wait, hold on. Let's just read. We go through everything. And we do this. If it's smaller or equal to mid. This is the current. +1. This is +1. So you do this minus this is smaller or equal to mid. But you did not consider the case where they could like use this is not right. Because you're reusing, right? You are reusing indices. Because you say I and I -1, right? And the next one, my bad. Smart. You see there are two I +1. Damn, it is an easy problem. Okay, I shouldn't say easy. It's not a difficult one. I know exactly what he does. This is not necessary. Okay? We just go through the entire thing. So the greedy part is trying to find the number of pairs whose value is smaller than the mid, right? And you sort it out, that's fine. And then every pair you check. Whenever a pair fits, you just keep it. And when you keep it, yes, of course, you cannot. So it's the same thing that bothers us yesterday. Is if we have 3, right? A1, A2. If we keep this, then we cannot use this. That was our initial problem. But the greedy says it does not matter. If this one is good and this one is bad, we're good. If this one is bad, this one is good, we will never pick this one, we'll pick this one. If both are bad, we won't pick. So the only issue that we have is if both are good. If this is good and this is good, then you say, if I pick this, I cannot pick this. But it's fine because among these 3, you can only pick one pair. So you either pick this pair or you pick this pair. It's the same thing. Therefore, we say we're just greedy, we pick the first pair, and then everything will be fine. So that, now when you think about, or you get that in mind, it's fairly straightforward, right? It's fairly straightforward. So we don't have to do, so we do not have to sort based on diff, right? Nor do we have to do a do an additional, right? Basically did additional binary search. We simply sort nums and go from left to right and find the total number of pairs that are smaller, whose diff is smaller or equal to the current mid, right? And the greedy is used here, right? Greedy is used here in that we always record the first pair that satisfies our requirement. Now, it does not matter if picking the first pair would preclude us from picking the immediate next pair that shares the middle value, that shares the value with the previous pair, because among these two pairs we can only get one, e.g. A0, A1, A2. If A1 minus A0 and A2 minus A1 are both valid, we can either pick A0, A1 or A1, A2. So which one we pick does not matter in the final count. Therefore, we can always pick A0, A1, and that will make the implementation very simple, very easy. Okay, so let's implement this. I will copy all that. Thank you very much. And then I'll say low, high equal to 0 and nums minus 1 plus 1. I'll do exactly the same here, with a slight difference. Okay, but we don't need this. We don't need this. All we need to do is current num used, num pairs, okay, equals 0. And we do for I in range len nums minus 1, okay. We say if, here is the trick, if nums I plus 1 minus nums I is smaller equal to mid, right, then we'll take it, right? Take pair I and I plus 1. So how do we take it? We say num pairs plus equal 1, okay? And then I plus equal 1, or that's why this has to be I equals, has to be a while loop. All right? In fact, let's do this. Let's get it out. Okay, let's do n. Yeah, plus equal 1, I plus equal 1, right? Now the trick is I plus equal 1 here. So this means, right, so we always increment I. We increment I one more time, an additional time, right? An additional time to avoid picking I plus 1 in the next round. So, which means if the current one is right, you picked it, we'll increment I increment 1, so we go to I plus 1. And on the outside, we increment again, which means the next time we pick, I becomes I plus 2. So you avoid picking this one. So that is the genius. This is very important, right? This is the most important part of this algorithm, right? This is very, very important. So So this is the key step of the algo. Okay, and then here it's going to be num pairs larger equal to p is too much, right? Then we can shrink it, right? We shrink it. If not enough, we do this. And I think this one's return low, right? Yeah, this one's return low. Okay, number 4. Dude, it's out of range. Of course, that should be -1. There we go. You wanna try the... Yes, I still have this one open. Alright, let's try this one. I use everything, I do this. I expect this to be much faster. Maybe not much faster, but it should be faster than the original one. Because I don't have an overhead of... I only sorted once, I don't have to sort it twice. Maybe 1,800? 1,500. Better. Shaved off 1,000 milliseconds. O(n), because this is O(n), log maximums. All right, so that's that. We're done. It's a good problem. Very good problem. I like it. Okay, minimum number of visited cells. All right, how much more do you want to do today? At least let's read through this and try to see if we have an idea. I want to end a bit early today. You're given a zero-indexed integer matrix. Your initial position is at the top left cell. Starting from cell ij, you can move to one of the following cells. Cells ik, with k is from current j to grid ij plus j. Rightward movement, and the amount of movement is determined by the value in the current cell. You can move to either that cell, those cells, so everything to the right up until this, and everything down up until this. Return the minimum number of cells you need to visit to reach the bottom right cell. Okay, so if I'm here, I can go 3 steps to the right or 3 steps down. So I say I go 3 steps down. And from here, I can move 2 steps to the right. Or I can move 1 step to the right. I move 1 step. And from here, I move. So the total minimum number of cells you need to visit. So it's 1, 2, 3, 4. Can we do this way? No, we cannot. If you move here, you can only go down 1. You go down 1, boom, you're dead. You are dead. Okay, let's see the size. You gotta be kidding me. So the complexity is in the order of OMN, maybe OMN log MN. The most we can do, okay? That's the most we can do. Need to figure out a way to... An idea? But most likely DP, right? I think it's very clear it's going to be DP. And because it's you can afford OMN complexity, so the DP is just going to be from every cell, what's the minimum number of steps to reach? Yeah, let's say from this cell, the minimum number of cells we need to visit. How about not including this? I think it's gonna be confusing, right? If you include this cell, let's say the minimum, like I'm here, right? If I'm here, I want to know the minimum number of cells I need to reach to go to here. So now I can try boom, 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 or boom, 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 right? Then I do this, then I need to know this, then I need to know this, I need to know this. When I know the minimum number of this, and then I plus 1, that'll be the minimum number from here. I do have to include, which means this will be 1. This is infinity because you can't reach, right? And let's draw it out, right? Let's draw it out. So it's a 4x4, right? We'll just draw it out 4x4. 1, 2, 3. 1, 2, 3. This position is 1. This position is infinity. This position is infinity. This position is infinity. Okay? And you're here. This is 4, right? And you can only go right or down. That's actually simplified the stuff. You cannot go down, so you're going to go right. And from here, I can say, I want to try this, but that's infinity. So then I try this, because I can go. And here is 1. So this one, the minimum that you can go from here is 1, right? And at plus 1, this will be 2. The minimum is 2. Then we try this, right? Try this. We have this, and we have this. And what we want is the minimum among these. The minimum among these. And the minimum among these is 2. So this position is going to be 3. And from here, for this cell, minimum among this and the minimum of this, because I can move my minimum of this and minimum of this. Oh. Okay, so this is going to be 3, right? And here is 2, so minimum of this. Do we have a way to find the minimum of, does BIT work on this? No, I don't think BIT works on this. What I want is the minimum value in a range. Minimum value in a range. Let's keep seeing. Let's keep moving on this. Now in this position, I want the minimum of these two, minimum of this. So this position is going to be 4, right? Because from this is going to be, yeah, and then here, that's going to be infinity. This position is infinity. This position is 3, right? Because its minimum is this. This position, 4, the entire thing, and the entire thing. So this position 4. This position is infinity. This position I can go 2, still infinity. This position I can go 4. So this position is 3. And now I'll go to this position. 3. So smallest among these and the smallest among these. This position is 4. So the difficult part is to find the smallest in a range. How do you find the smallest in a range? You can do, Jesus, you're gonna do segment tree on this. I doubt it. I doubt it's segment tree, but I know but the smallest in a range. What's the algorithm for smallest in a range? I can do prefix sum, the sum of a range, But that doesn't help. I can do smallest. Wait, does BIT work on smallest in a range? No, BIT only do smallest or biggest from the start to a value. From a start to a value. It does not work for a range. Lordy. Is this sorted? Do you think every row and every column is sorted? Well, if you think about it, if you are at a certain value, right? You just in a giant, doesn't matter. You have a giant thing, and you are at this position. You're looking at the smallest thing this and the smallest thing this, and you put your value here, right? If the smallest is here, then you'll be one bigger than this. If the smallest is somewhere else, what if we have, let's say, but everything is going to be hold a second. Would it be possible that we have a value let's say this is a 1, and then we have a bunch of infinities, and then you got here, right? And here you have, let's say, 2, 3. Okay, let's say here, this position, you need 3 steps to go. Yeah, it could be. Right? It could be. We can design it. Like these can be infinity, and this can require 2 step. This can require 1 step. You know what? Even better. That should be 3. Hold on. Because this is a 1 step. So at minimum, this will be 2 step. Okay, and this will be 2 steps. This will be 3 steps. This will be 4 step. Let's say this will be 5 steps. Yeah, like this, right? Let's do it one more time. We have 1 step, 2, 3, 4, 5, infinity, and infinity, 2. Infinity. What is this position? This position is going to be 3. If I can reach these 2, and if I can reach this, it's going to be 3. And this is no longer sorted. And this is possible because this is just going to be 0. And this is going to be 1. Right? And this will be 2. And this will be 3. Done. Right? We can even try it. I think we can even try this. So let's say we're gonna design it this way. 1, 2, 3, 1, 2. This is 0, 0, 0, 0, 1, 1, 1, 1. 3, 0, 0, 3, 2, 2. Yep. Let's try this. 3, 1, 1. 0, 0, 1. 0, 0, 1. 2, 0, 0. Yep, 3, right? Now the question is exactly how to find minimum in a range. without implementing a segment tree, because here you're talking about segment too many. Dude, like how many segment tree are you talking about? Every single row and every single column needs to be a segment tree. Otherwise, you will have to go through the whole thing. That's not possible. Okay, I'm not gonna just pound it because I don't know. Find minimum value in any range of an array. I don't know. I don't think this is the one we're looking for. Min-max range queries. I think that's the one. Yes. Yes. Yes, that's the one. No, don't do segment tree. Can we do something else? Oh, that is a very fast segment tree. I mean, if you look at this, it doesn't seem that bad, right? We do have the define node. Wait, hold on. Segment tree, you can do it. You can do it as an array, right? Segment tree can do it as an array. Yeah, I think we have to do segment tree on this one. But still, every single row you need a segment tree. Right, so you start. Okay, what's segment tree? Segment tree, you have an initial range, right? And then you will do, gosh, come on. I always dread segment tree every single time. You have to do it. Okay, let me think again. Segment tree. It's gonna be an array. Okay? And it's just gonna be indices. And you'll have update.
Did you feed them?
Oh, not yet. I'll do it right now. Don't worry, I'll do it right now. Alright, I'll think about segment tree tomorrow. That will be it. See you guys tomorrow. Adios.